Hey guys, so we're going to continue the discussion of finding probabilities of compound events. So today we're going to work on probabilities. We're going to do probability problems that have the word and in there, and then not. So we did ors already, so let me write ors, but we did that already. So we're working on these today. And then the very last one is at least one. So if you're finding a probability and the problem has the word and in there, okay, you're trying to find the probability of an and, then there's two formulas for finding the probability of an and. The formula you use depends on if the events are independent. Remember that for or, there's two formulas depending on if the events are disjoint. Okay, there's a short formula, a longer formula. For and, there's two formulas depending on if the events are independent. Okay, so if the events are independent and you're trying to find the probability of an and, then the formula is probability of the first event you see in the parentheses times the probability of the second event you see in the parentheses. It looks a lot like the or formula, but instead of adding, you're multiplying. It's called the multiplication rule. So let me say it again. To find the probability of an and, if the events are independent, okay, you do the probability of the first times the probability of the second. So just say it to yourself like that. Probability of the first times probability of the second. Now, if you're trying to find the probability of an and the events are not independent, then use the slightly longer formula. It's the probability of the first event you see in the parentheses, times, and then over here it's probability of the second given the first. Remember, this means you read this as given. That's a conditional probability. And that's why I had to teach you conditional probability first, because if we're going to use this formula, it has a conditional probability in there. Okay, so let me just say that whole thing one more time. So if you're trying to find the probability of an and the events are not independent, it's the probability of the first event times the probability of the second event given the first event. So probability of the first times probability of the second given the first. And if you're doing a problem and you don't know if they're independent or not, so the question is, are they independent? Then the deal is just use the bottom formula. The bottom formula can be used always, okay? But if you're doing a problem and you know for sure they're independent, then use the top one. It's shorter, a little easier to think about. You don't have to worry about a conditional probability. But again, if you're not sure if they're independent, then just use the longer formula. The longer formula always works. All right, so what we're going to do is we're going to practice probabilities of ands like crazy. So here we go. Example 13. So in this example, we're drawing one ball out of this bag, and it says to find the probability of A and C. Okay, let's see what A is. So A is even, and C is yellow. This is saying find the probability you get a ball that's even and yellow. Okay, now there's two different ways to do this problem. Just like when we did OR problems, there were two ways to do it. When you do AND problems, sometimes there's two ways to do it. You can use the AND formula, and you can also do it using the absolute value form at the beginning. So I think just for this one example, I will do it two ways, but after that, I'm going to just do it using the AND formula. So it's called solution one here. Okay, so solution one is if you use the absolute value formula right at the beginning and not the AND formula. So the absolute value formula goes like this. Whatever you see in the parentheses, you write on top with an absolute value around it. On the bottom, write absolute value of S, and then you start counting. You have to count how many things are in A and C. So how many are even and yellow? That's pretty easy to see. If you're not able to see it, another way to do it is you can write down what A is. A is even, so 2, 4, 6, 8, 10. C is just the yellows, so 2 and 3. And then A and C, the event A and C, so I'm making a list. You have to list the things that are in both. You can look at those two lists and figure out what's in both. So what number or numbers are in both? Someone tell me.
2.
2, just 2. Okay. And how many things are in that? Because absolute value of A and C means count how many things are in that event, and the answer is there's just one thing in there. And then there's 10 things in the bag total. And that's the answer to that, doing it that way. So again, you could just count how many of these are even and yellow, just one. Or you could do it this way. List the evens, list the yellows, and then list the ones that are both, and then count how many things are in there. So that's okay. So that's one way to do it. That way of doing it, use the absolute value formula as your first step, and then you just count and you're done. Okay. Second way of doing it, using the AND formula. There's two AND formulas. Let me put this in black here. Oops, sorry. Probability A and C. Okay, so if we can use an AND formula, remember there's two AND formulas depending on if the events are independent. So I first want to know if these events are independent. Now, there's only one time you know for sure without doing any work that the events are independent. The only time you know if you're doing a problem where you're drawing more than once with replacement. In this problem, we're only drawing once though, so it's not that situation, okay? So how do I know if they're independent? Well, either you have to do a separate calculation first to see if they're independent, which would, the calculation would go something like this, and you'd have to figure out if these numbers are the same, and then you would know if they're independent or not. Okay, so you could do a whole separate calculation to see if they're independent first. But I don't advise you to do that, but you could. Or what you can do is you can say, well, you know what? If I don't know if they're independent, I'll just use the longer formula because I can use that whether they're independent or not. So long story short, if you're not sure if they're independent, again, you could either first figure out if they're independent and then decide what formula to use, or just always use the bottom one, the longer and formula. So I'm not going to do this calculation. You could if you want, but I'm not going to do it. Instead, let's just go ahead and use the longer and formula. So when I ask you, are these events independent? Your answer is, I don't know. And so you're going to write independent with a question mark on above the parentheses. That's you telling me you don't know if they're independent, and for that reason, you're going to use the longer and formula. Now here's how the longer and formula goes. It's going to be the probability of the first times probability of the second given the first. Okay, so probability of the first event times probability of the second event given the first event. Okay, and now we got to find these two probabilities. Let's start with this one. Normally, when there's a conditional probability involved, I don't write any other formulas after, so I'm just going to go ahead and figure out what these two answers are. So like, I'm not going to write absolute value of A over absolute value of S, so I'm just going to leave off the formulas here. And okay, probability of A. I'm trying to find the probability of getting an even. This is a regular probability. It's not a conditional probability. So the bottom number is 10 because there's 10 things in the sample space total. And then on top, how many even numbers are in the bag? 5 even numbers in the bag. So that's probability of A. Any questions so far? Remember, to find probability of A, it's not a conditional probability. So the sample space is the entire bag. So how many things total in the entire bag on the bottom? How many evens total in the entire bag on top? Okay, but then this next probability is a conditional probability. So what's going to happen is the sample space is going to change for that one. Okay, so the bottom number will not be 10. And again, this is how you do a conditional probability when you're drawing one time. So this is what I said last time. This is what you do. You put your hand in the bag. So pretend I put my hand in the bag. I draw one ball. I show it to you, but I don't look at it. And you give me this information. You say, hey, Greg, you drew an even number. You give me that information. Once you told me it's an even number, some numbers in the bag are not possible anymore. So I want to figure out what the new bag is. So you think about the new sample space. I'll write it over here. You said, oh, Greg, you drew an even number. Okay, I'm like, okay, then it must have been 2, 4, 6, 8, or 10. Okay, so my new sample space has 5 things in it. So you put 5 on the bottom. Remember, bottom is always how many things are in your sample space. But in my new sample space, there's 5 things on the bottom. And now I'm trying to find the probability of C. Let's go read what C is. Okay, C is a yellow. So I have to count how many yellow balls there are, but do not count them here. You count them in your new sample space. And in the new sample space, only the 2 is yellow. Okay, because 3 is not in there, so only the 2, so 1. So you put a 1 there. And then you just multiply these fractions. Now, again, I'm not going to teach really how to multiply fractions. If you don't know how to do it, you could just multiply them on your calculator. It's not a big deal. But I'll just say briefly how you do it, but I'm not going to spend a long time on it. But the way you multiply fractions is you multiply straight across. So you multiply the 5 and the 1, you get 5. And on the bottom, you multiply the 10 and the 5, and you get 50. So the answer is 5 out of 50. If you simplify this, you get 1 out of 10. I'm simplifying it so you can see that the answer matches the answer that's over here. Also, if you know other things about fractions, like if you knew these 5s cancel, which they do, then you can see there that the answer is 1 out of 10. But again, it doesn't matter how you write your answer. You can write your answer as a fraction, decimal, percent, anything you want. So just multiply them on the calculator or whatever you want to do. Multiply them, but multiply them correctly and get the answer. And that's how you do probability of A and C using the AND formula. Any questions? Okay, let's keep going. We're going to do a bunch of problems. Okay, so one more on this example. So still the same experiment. We're drawing one time out of this bag. And again, I'll do this problem two ways. I think this will be the only example where I do it two ways. Again, make sure you know how to do it both ways, because as I said, some problems you can, both ways will work. And in that case, you can pick whichever one you want and do it that way. But in some problems, only one way will work depending on the information that's presented to you. And so you got to pick the way that will get you the answer. Okay, so you have to make sure you know how to do both ways. And again, once in a while you get lucky and you can do both ways, then just pick the way you want. So this first solution way, I'm going to use the absolute value formula. So the absolute value formula goes like this. All right, so B and E. Okay. So we have to, so on top we have to count the balls that are prime and larger than 6. Okay, okay. So which ones are prime and larger than 6? You can just see 7 is prime and larger than 6, and that's the only one. So the top is going to be a 1. Okay. Or if you don't want to read the words and do it like that, one way you can do it is you can write down what B is. B are the primes. 2, 3, 5, 7 are the primes that are in this bag. E are the numbers larger than 6. That's 7, 8, 9, 10. So I'm writing events over here. And then I'm going to find what B and E is. Remember what that means. That's the stuff that's in both. And if you look at these two lists, the only thing that's in both is 7. And then this says count how many things are on this list. One thing. Okay. Anyway, so that's how you do it the first way. Any questions? Okay. Then the second way of doing it is if you use the AND formula. And if you're going to use the AND formula, you're only going to use the AND formula. Oops, solution 2. You're not going to use any absolute values after. Okay, so here we go. Probability of B and E. If you're going to use an AND formula, there's 2 AND formulas. So the one you use depends on if the events are independent or not. So I first need to know if the events are independent. If you're doing something once, drawing one ball out of a bag, flipping one coin, drawing one card out of a deck, you don't know if they're independent without doing some extra work, and I don't want to do the extra work. So instead, we're just going to write that we're not sure if they're independent. I'm not going to find out. If you're dying to find out, you can, but I'm not going to find out. And because I'm not going to find out, we're going to use the longer AND formula, which goes like this. Probability of the first event that you see in the parentheses times probability of the second event given the first event. Probability of the first times probability of the second given the first. And again, once you write a formula with a conditional probability in it, I don't have you write any other formulas. So you go straight to the to finding the answers now. Okay, probability of B. Okay, so this is a regular probability. Again, what I'm doing really, I'll write it down, but I'm not going to write this formula down there. This is what I'm doing in my mind. Okay, I'm thinking, okay, how many things are in the sample space and how many things are in B? Okay, how many things are in the sample space? 10, because for this is a regular probability. The sample space is the entire bag. 10 things total in the entire bag. How many things are in B? What was B again? Prime number. How many prime numbers in the entire bag? There's 4. The 2, the 3, the 5, and the 7 are the prime numbers. So there's 4 things. This probability, 4 out of 10. Is everybody with me on that much?
Yes.
Yeah.
All right. Then to get the other probability, this one is a conditional probability. What I know about that is the sample space is going to change. So the bottom is not going to be 10. The sample space is going to get narrowed down. Some balls are going to be kind of thrown out of the bag. So this is how we think about it. When you draw once, imagine I put my hand in the bag, I draw a ball, I don't look at it, but I show it to you. You give me this information. You say, hey, Greg, you drew a prime number. So you're not telling me what it is, but you're telling me it's prime. As soon as you tell me it's prime, some of those things in the bag are not possible anymore. It's got to be a 2, 3, 5, or 7. Once you tell me it's prime, those are all the primes. So I want you to think for the rest of this probability here that this is the bag we're drawing out of and not this. So if we're drawing out of this bag over here, there's 4 things in there, so 4 goes on the bottom. And then to get the top number, we got to find the probability of E. That means we have to count how many things are in E. E are the numbers that are larger than 6. You have to count the numbers that are larger than 6. Again, do not count them here. Count them here in the new bag. And there's one number in there that's larger than 6, just the 7. Okay, so that's how that probability goes. Then you just multiply straight across. So it's 4 over 40. Or you can just cancel the 4s. If you know that you can cancel the 4s, you get 1 out of 10. Again, if you write 4 out of 40, or if you write as a decimal or a percent, any of those are fine, as long as it's equivalent to 1 out of 10. So I'm showing you that the 4s cancel so you can see that these match. They better. I did the same problem, so I better get the same answer. Okay, and that is, I guess, the end of the story on example 13. Any questions on example 13? Okay, so understand that when you're doing AND problems, a lot of times, not always, but a lot of times you're going to be calculating a conditional probability. And I mentioned last time that when you do conditional probabilities, there's different ways of thinking about it if you, depending on if the problem says you're doing something once or you're doing something more than once. So in example 13, we were doing something once. We're drawing one time out of this bag. Okay, but the next couple of examples, we're going to do something more than once. So in this example, we still have the same bag, but now it says we're going to draw 2 balls from the bag, one by one with replacements. We're drawing 2 times, one at a time with replacement. And ask you to find all these probabilities down here. Okay, let's start with this one. Probability R1 and R2. Okay, for the next few problems, I'm only going to do the problem one way. I know I keep doing things 2 ways, but for the next few, I'm just going to use the AND formula, so we practice the AND formula more. All right, also, you notice that these events have little numbers on the bottom, subscripts, right? I want to make sure you guys understand what that means. This is very important, and especially when you're doing quiz problems and exam problems where you're drawing or doing something more than once, I need to see these subscripts. R1 means the first ball. Remember, we're drawing 2 balls. It means the first ball you drew was red, okay? This R2 means the second ball you drew was red. We're drawing 2 balls, so this is saying find the probability that the first ball you draw is red and the second ball you draw is red. Okay, so please make sure you put the number down there. That number lets me know which draw you're talking about. R1 means the first draw resulted in a red. The 2 on the bottom here lets me know the second ball that you drew was red. Okay, and again, it's an AND problem. Okay, there's 2 AND formulas. The one I'm going to use depends on if the events are independent or not. So I need to know if the events are independent. Are these events independent, yes or no?
Yes.
Yes, you're right. How come?
Because it has replacement?
Yeah, we're drawing more than once. We're drawing 2 times with replacement. That is the only situation where we know that the events are independent ahead of time. So what you're going to do is you're going to write the word independent up on top with a check mark, meaning you know that they're independent. Okay. All right, so sometimes I'll give problems where you're drawing once and a student will say, is it with replacement or without replacement? And I'll say, that doesn't matter because we're drawing once. But when you're drawing more than once, then it matters. So we're drawing more than once with replacement, the events are independent. Because they're independent, we use the shorter AND formula. The formula goes like this: probability of the first times probability of the second. No conditional probability, it's just probability of the first times probability of the second. That's a little bit shorter than the other formula that we used. Okay, now I'm going to find each of these probabilities here. All right, let's focus on the first one. So whatever is after the symbol P, that's what we're finding the probability of. Probability the first ball is drawn, that was drawn, is red. I need you to think, because you know, what are we doing? We're drawing 2 balls, right? We're going to draw 1 ball, look at it, we're going to put it back, mix the balls up, and then we're going to draw another one. So it's this whole procedure you got to do before you're done drawing 2 balls. But when it says probability R1, I want you to imagine we're about to draw the first ball. We haven't drawn it yet. You're at the point in the procedure where you're about to draw the first ball. So we haven't drawn anything yet. We're about to draw the first ball. What's the probability? The first one is red. So when we go to draw the first ball, we're drawing out of this full bag over here. So the number of things in the sample space is 10, and that goes on the bottom. And on top, you have to count how many are red, which is 1. So we got 1 out of 10 for that one. Is everybody clear on that?
Yes.
All right. And then to find this probability, you need to think about it like this, because right next to the P, it says R2. I need you to imagine that we're about to do the second draw. So we've already drawn the first ball. We're about to draw the second one. It says we're going to draw 1 at a time. So we're about to draw the second one. Well, what happened? We drew the first ball. We looked at it. We put it back, right? Because with replacement. We mix them up, and we're about to draw the second ball. When you're about to draw the second ball, you have to ask yourself, what does the bag look like when you're about to draw the second ball? The answer is the bag will look just like this because after you drew the first ball, you put it back. So the bag is, everything in the bag is still there when you're about to draw the second one.
So then the sample space stays the same on the second draw because it's being replaced?
Exactly. Sample space stays the same on the second draw because you put the first ball you drew back in. That's right.
Okay.
Okay, so then tell me, what's the probability on the second draw you get a red? What's the answer?
One.
Not 1, but 1 is the top.
10.
1/10.
1/10, right. Okay. Yeah. And then you multiply straight across. 1 times 1 is 1, 10 times 10 is 100, and that is the end of the story on that example. I mean, we got more in example 14, but that's the end of this one. Any questions? All right, let's do a couple more like that. All right, again, what am I saying here? We're drawing 2 balls, one at a time with replacement. This is saying, what's the probability the first ball you drew is blue and the second ball you drew was green? Okay, so that's the question. And again, this 1 means on your first draw you got a blue. This 2 means on your second draw you got a green. All right, so now to find this probability, again, there's 2 AND formulas. The one I use depends on if the events are independent or not. So I need to know, are these events independent?
Yes.
Yes.
Okay, what's the reason that they're independent? So the answer is yes, they're independent. Why are they independent?
Because it has a replacement.
Yeah, but it's also, we're drawing more than once. So we're drawing more than once with replacement. So it's got to have those 2 things, more than once with replacement. Then we know they're independent. Okay, since they're independent, the formula is, use the shorter one instead of the longer one. It's the probability of the first times probability of the second. No conditional probabilities anywhere. Okay. So now we have 2 probabilities to find. And again, and then we'll multiply them after. Let's look at the first one. Probability the first ball you draw is blue. You have to ask yourself, what does the bag look like when you're about to draw the first time? When you're about to draw the first ball, the bag is the entire bag that you see here. I want to know they're probably getting a blue. So the bottom is going to be how many things are in the bag total. The top is going to be how many blues are in the bag total. What's the answer for that probability?
4 and 10.
4/10, right? All right. Then to get this probability, you have to ask yourself how the bag changes. We're about to draw the second time. So when you see a 2 here, think we're about to do the second draw. So what has already happened? We've already drawn the first one. We drew a ball because we're drawing 2. We've already drawn the first one. We looked at it. We're like, yeah, that's nice. We put it back. We mix them up, and we're about to draw the second time. What does the bag look like when we're about to draw the second time? Looks exactly the same because I put the ball back. Whatever ball I drew out first, I put it back. So the bag looks exactly the same. And now I want to know the probability when I draw from this bag, I get a green on the second draw. What's the answer?
3 out of 10.
3/10.
3 out of 10, yeah. Okay, and then you just multiply straight across. 4 times 3 is 12. 10 times 10 is 100. And that's the end of the story on this one. Questions? All right, one more on this one.
Why it's independent?
Oh, question? Sorry, say it again.
Can you explain why it's independent again?
Because we're drawing more than once with replacement. When it says drawing, anytime you're doing a problem where it says you're doing something more than once with replacement, they're independent.
Okay, thank you.
No problem. Let me say a little more in case that's not exactly what you meant. I mean, maybe I didn't answer exactly the question you asked. So let me put it to you like this. If you draw, let's say you draw a ball, and the first ball you draw is red. Okay, and then you leave it out. You don't put it back in. Then the chance of getting a red the next time, there's no chance. Because you drew the red out the first time, there's no way you can get another red. There's no other reds in there. Okay. Whereas if you draw the 3 out the first time, what's probably get the red the second time? You could get a red the second time. So the second outcome depends on the first outcome. Okay, the first, whatever comes out on the second draw depends on what came out on the first draw because you didn't put it back. But if you put it back, then the chance of getting a red is the same every time. You keep putting it back. Okay, so the idea is the probability of getting a red on the second draw does not depend on what the first ball that you drew was, because whatever you drew on the first one, you put it back. So long story short, when it says with, so I'll just say now what I said to you earlier. If it's with replacement, that's the only time you know that the events are independent. Okay, other questions? Okay, let's go to the next one here. Okay, so this is an and for a problem again, but I need to change this a little bit. Up on top it says we're drawing 2 times, but it shouldn't say drawing 2 times, so we need to change this to 4 times. So just for this example, we're drawing 4 times from the bag, 1 at a time with replacements. And what am I asking? I'm saying, what's the probability the first ball you draw is green, and the second ball you draw is yellow, and the third ball you draw is blue, and the fourth ball you draw is blue. Okay, so if you were to draw 4 times, 1 at a time with replacement, what's the probability the first one is green, and the second is yellow, and the third is blue, and the fourth is blue? That's what I'm asking. All right, it's an and problem. Again, there's 2 and formulas to use, that you can choose from. The one you're going to use depends on if the events are independent. They are indeed independent, again, because we're drawing more than once, in this case 4 times, with replacement. So they are independent. So you're going to write independent with a check mark above the parentheses. Now, the formulas that I gave you for and earlier, there were 2 formulas for and, but both those formulas only had 2 events in the parentheses. But now I have 4 events, right? 1, 2, 3. I have 4 events in the parentheses. So what you need to do is you need to take the formula and extend it to more than 2 events. Both of those formulas can be extended to more than 2 events, which it's pretty easy. Let's try to make a guess what it's going to be. What would it have been normally? It would have been probability of the first times probability of the second. But because we have 4 events, we got to keep going. What's the next part going to be? Any guesses?
Probability of B3.
Yeah, so times probability of the third, which is B3. And then what?
Probability of B4.
Yeah, and you're multiplying them all, okay? So instead of it just being probability of the first times probability of the second, you have 4 events in there. It's probably the first times probably the second times probably the third times probably the fourth. If you had 7 events in there, it'd be probability of the first times probably the second times probably the third times probably the fourth times probably the fifth times probably the sixth times probably the second. So it's 7th. So you just probably each one and you multiply them all together. So that's just extending the formula when you have more than 2 events. Okay. Each one of these probabilities is about a different draw. This says those are probably the first draw. On the first draw, you get a green. And the way you figure out is you have to ask yourself, what does the bag look like when you're about to draw the first time? When you're about to draw the first time, the bag is the full entire bag. What's probably get a green on the first draw? What's the answer?
3/10.
3/10. Again, the bottom number is always going to be how many things are in there total. The top is how many greens are in there. So 3 out of 10. To get the probability, the second one is yellow. You have to ask yourself, if we're about to do our second draw, at that moment, what does the bag look like? And the answer is the bag looks the same, because after we draw the first one, it was whatever it was, we put it back in, and now we're about to draw again. So when you go to draw the second one, probably getting a yellow, well, the bag looks like the full entire bag. So what's the probability of getting a yellow on the second draw?
2/10.
2/10. All right, let's go to the third one. This is talking about the third draw. So I need you to pretend we've already drawn 2 balls out of the bag, and you're about to draw the third one. When you're about to draw the third one, what does the bag you're drawing out of look like? It looks the same again. Why? Because you drew the first one, you put it back. You mix them up. You drew the second one, you put it back. And now you're about to draw the third one. Every single time since you put it back, the new bag looks the same as the old ones. What's probably getting a blue on the third one?
4/10.
Okay. Who can tell me the probability of getting a blue on the fourth one?
4/10.
4 out of 10. The fact that all the denominators are 10 tells me that every single time we have a full bag with 10 numbers in there. Okay? You'll see how that's going to change in the next example. But yeah, you do that. And then you just multiply straight across. 3 times 2 times 4 times 4. I think that's 96. And the bottom 10 times 10 times 10 times 10 is 10,000. And that is the answer to that one. Any questions? All right, so that's example 14. Okay, let's do another one. So now example 15. Look at the difference in example 15. We still have the same bag. We're drawing 2 balls one at a time, one by one, but now it's without replacement. What does without replacement mean? It means we're going to draw the first ball, then we're going to leave it out, and then draw the second one without replacement. We're not putting it back. We're not replacing it. Okay? And I have all these probabilities I'm asking you to find. I'm not going to find them all. I'm going to skip a couple, but we'll do most of them anyway. All right, here we go. First one, probably R1 and R2. What am I asking, first of all? I'm saying if you were to draw 2 balls from the bag, one at a time with replacement, what's the probability the first one is red? That's what that means. And the second one is red. That's the question. What's probably the first ball you get is red, and the second ball you get is red. Okay. So now, it's an AND problem. There's 2 AND formulas. The one I use depends on if the events are independent or not. So I need to know if the events are independent. Are they independent?
No.
No? Okay.
Wait.
Since we're drawing without replacement, the only time you know for sure that they're independent if we're drawing with replacement. If we're drawing without replacement, they're probably not independent. And if you're not sure, the point is we're not sure. Okay, so you're going to write independent with a question mark. Either you're going to be sure or you're not going to be sure. Pretty much, they're probably not, but just write independent with a question mark on top. And because I don't know if they're independent or not, we're going to use the longer AND formula, which goes like this. It's the probability of the first times probability of the second given the first. Okay, tell me this. What's the probability on your first draw you get a red?
1 in 10.
1 out of 10. Cool. All right. Now, this is a conditional probability. Conditional probability, the sample space is going to change. So again, whatever's after the P, it says R2. So I want you to pretend you're about to do your second draw. And when you're about to do your second draw, the question is, what does the bag look like now? The bag will not look like this full bag anymore because this happened, okay? Whatever's after the vertical line is new information. In other words, the first ball you drew was red. You took it out, and then what happened? You left it out, okay? And you're about to draw the second time. So you have to ask yourself, right before you draw the second time, what does the bag look like? Well, it's going to look like what you see here, but we've already drawn a red. So I'm going to just scribble this out like it's not there anymore. So this is the new bag we're drawing out of, this bag now. Okay, it's a new modified bag after we're given the new information. So we drew the first one out, it was red. So this happened. And it stays out. And now I'm asking what's the probability to get a red on the second one? Well, bottom number is going to be, so the number down here is going to be how many things are in the new bag. How many things?
9.
9, right? And the top number is going to be how many are red in the new bag. How many?
0.
0. Yeah. There's no reds left. And then you just multiply those and you get 0. If you were to multiply straight across, you'd get 0 over 90. But 0 over 90 is 0. So that's the probability there. No chance. There's no chance for that to happen. And that should make sense too, because if we just go back to the beginning here, I'm saying you're going to draw 2 balls. What's the probability they're both red? The first one's red and the second one's red. Well, if the first one you draw is red and you leave it out, you can't get a red on the second one. So it's not possible that you draw 2 reds out of this bag if there's only 1 red in there, unless you put it back in first, but we're not. Okay, that's that one. We'll do more. Any questions so far? All right, let's do the next one. Okay, so again, we're drawing 2 balls from the bag, one at a time, without replacement. This is saying what's the probability the first one you get is blue and the second one you get is green. Okay, again, it's an AND problem. There's 2 AND formulas. The one you're going to use depends on if the events are independent or not. I don't know if they're independent because it's without replacement. So we're going to write down independent with the question mark, like I don't know if they're independent. And because we don't know, we're going to use the longer and formula. And it goes like this, probably the first times probability of the second given the first. Okay, so we have two probabilities to find. When you're finding this one, you need to think you're about to do the first draw, because right after the P symbol it says B1, there's a 1 there. You're about to do your first draw. When you find this probability, right next to the P it says G2, so you're about to do your second draw. So you're at different points in the drawing process, okay? But for this first one here for now, when you draw the first ball, you're drawing out of the full entire bag. What's the probability you get a blue? What's the answer?
4/10.
Okay. And now to get the second probability, the sample space is going to change because this has already happened. So I've already drawn a ball. It was blue. It's been removed and it's not coming back in. And I'm about to draw again. So I want to think, okay, what does the bag look like when I'm about to draw my second draw? Well, we remove the blue. So you just have to scribble out one of the blues. It doesn't matter which one. I'm just going to scribble one out. So, and then this, pretend that this is the new bag we're drawing out of. Okay, so I want to know what's the probability of getting a green out of this new bag. Probably getting a green out of the new bag. What's the answer?
3/9.
3/9. Yeah. And then you multiply straight across. 4 times 3 is 12. 10 times 9 is 90. And again, if you don't remember that you need to multiply straight across, just type 4/10 in your calculator, type 3/9 in your calculator and multiply it, and then you can write the answer as a decimal or percent. Any of those are fine. Yeah, that's that one. Questions so far? All right, let's keep going. Let's do this one. Still same example. We're drawing 2 times, 1 at a time without replacement. Again, it's an and. There's 2 and formulas. The one you use depends on if the events are independent or not. Again, I don't know if they're independent, so we're going to write independent with the question mark. The only time I know is if it's with replacement. Okay, if it would have said with replacement, but it doesn't say that. It says without replacement. So I don't know. So longer and formula, and the formula is going to go probably the first times probability of the second given the first. Okay, this says the probability the first ball you draw is blue. What is that?
Over 10.
4/10.
Wonderful, 4/10. Okay, and again, this is a conditional probability. This one, the sample space is going to change, so the bag is going to change. So we're about to draw the second time. That's what that says. But what has already happened? This already happened. So we've already drawn a blue one out. Okay, and we don't put it back because we're drawing without replacement. So I need you to imagine a new bag where one blue has been drawn out. I'm going to just scribble out one blue one. And now we're about to draw our second draw from this new modified bag. And from the new bag, what's the probability I get a blue? What's the answer?
3/9.
3/9. 3 blue, 9 total in the new bag. And again, you multiply straight across, 12/90 for that one. Questions on that one? Okay, I'm going to skip this one just because I need to skip some stuff, but it's similar to the other ones. But let's go to this one. Now, focus really hard on this, okay, because this is the kind of place on a quiz and an exam where students get the notation, get the formula wrong, basically. So I want you to pay super close attention to how to write the formula. First of all, let's pretend this doesn't say you're drawing 2 balls. For this one, we're drawing 4 balls. I'm drawing 4 balls from the bag, one at a time without replacement. And I'm asking, what's the probability the first one is green, and the second one is yellow, and the third one is blue, and the fourth one is blue? Okay. Now, again, it's an and question. There's 2 and formulas. The one you use depends on if the events are dependent. And again, I don't know if they're independent because we're drawing without replacement, so we'll write that. So we have to use the longer and formula. Now, the longer and formula is going to go, maybe I could squeeze it in here. So We have these long AND formulas, but again, the AND formulas that I gave you only had 2 events in there, but now I have 4 events. We have to extend the formula to more than 2 events, to 4 events in this case. Now, when they are independent, like the last example, example 14, it was real easy to extend it, but when they're not independent, it's a little harder. So everyone check out how it's going to go. Well, let's start it out. What would it have been normally? It would have been probability of the first times probability of the second given the first. But we got to keep going because we have 4 events. So if you have 4 events in the parentheses, you're going to get 4 terms being multiplied instead of 2 terms. Times, and what was it when they were independent? It was probability of the first times probability of the second times probability of the third times probability of the fourth. But that's when they are independent. If they're not independent, then each probability is going to have a condition afterwards, except for this first one here. So it's probably the first times the probability of the second given something, and that's going to be times the probability of the third given something, and that's going to be times the probability of the fourth given something. So probably the first times probably the second given something, times probably the third given something, times probably the fourth given something. So this next one is going to be probability of the third given something. And now let me just tell you what goes in here. So check it out. The rest of these are going to have ands in here. Goes like this. We're doing the probability of the third right there. Probably the third given, what goes in the given? Everything you see before this box. So you're going to write G1 and Y2. Don't write this and symbol. Let me say that again. So when you're trying to find when you're on the term where it's probably this, you're going to write given everything you see in the parentheses before it. So G1 and Y2. So it's like this. Probability of that. Okay. Then probability of that given that. Then the next term is going to be probability of that given all that. And then hopefully you can guess the last one. The last one's going to be probability of this, probability of B4 given. Can you guess what goes after the given, after the line there?
B3.
Not just B3. Everything you see before the symbol B4. So not just B3, all of this. Okay, so it's going to be G1 and Y2 and B3. And make sure you remember that these have ands in them. Okay. You guys following what I'm saying? Does anyone get what I'm saying?
Yeah.
All right. So after you got the formula down, make sure, again, when I grade things like this on exams especially, I look for a lot, right? I look for notation. The notation is given to you in this problem, but otherwise I look for notation. I look for you writing letters if I don't write them, but I wrote them here. And I look for formulas and then the answer. So the answer is only part of the work. So I'm looking for all this stuff. So really make sure you guys get this. And of course, if you write the formula right, but you get the answer wrong, you're going to get credit for getting the formula right because that's an important part. That's what I'm testing you on. So make sure you completely understand how to write the formula. Now we got to find all these probabilities. This is probably the first ball we draw is green. Someone tell me the answer.
3/10.
3/10. Yeah. For that first probability, we're about to do our first draw. What does the bag look like? Entire bag. And then you start counting. 3 green, 10 total. Okay. Now this one, the bag is going to look different. Why? We're about to draw our second one. The first ball we drew was green. We have to remove a green. Okay, here I go. I'm going to remove a green. It doesn't matter which one. Let me just remove this one. And now you imagine we're drawing out of this new bag that has only 9 things in it. What's probably getting a yellow out of the new bag?
2/9.
Yeah, 2 yellow, 9 total. Okay, now let's go to this probability here. This has already happened. Whatever's on the left, I'm sorry, on the right of the vertical line, that's already happened. So what's already happened? We've drawn the first one, it was green, and we drew the second, it was yellow. First one was green, and the second one was yellow. That's already happened, and we're about to draw the third one. So you have, before you figure out the answer, you have to go, what does the new bag look like? Well, it's the old bag, but 1 green has been removed and 1 yellow has been removed. I already removed a green. I'm going to remove a yellow now. Any yellow, it doesn't matter. Let me remove this one. And now the bag looks like that. When you draw from a bag like that, that'll be on your third draw. You'll draw from a bag like that. What's the probability you get a blue? What's the answer?
4/8.
3/8.
There's 4 blue, 8 total. Is everybody with me so far?
Yep.
Yeah.
Okay, let's go to the last one. So for the last one, we're about to do our 4th draw. That means we've already drawn 3 balls. And what happened when we drew the 3 balls? This is what happened. The first one was green, and the second one was yellow, and the third one was blue, and they've all been removed. So I have to remove those. So let's see, we already removed the green, we already removed the yellow. I have to remove a blue. We just cross off one blue here. Doesn't matter which blue. Let's say we cross that off. And that's what the new bag looks like. So every time you got to go, what does the bag look like that I'm drawing out of? It looks like that. And now I want to know the probability of getting a blue out of this new bag. What's the answer?
3/7.
3/7. Yeah. And then you multiply straight across. Let's see. It looks like, here, let me do my calculator. 3 times 2 times 4 times 3 looks like 72. And the bottom number looks like 5,040. If you do 10 times 9 times 8 times 7, 5,040, and that is the answer. Again, you don't have to multiply straight across. Just put the fractions in your calculator and just multiply them. And that is example 15. Any questions on example 15? All right, so again, remember, when you're doing conditional probabilities, like these are conditional probabilities, there's 2 ways to think of them, depending if we're drawing one time or more than once. So example 14 and example 15, we were drawing more than once. Whereas example 13, we're drawing only once. So there's a slightly different way of thinking about conditional probabilities. Let's do example 16. Okay, this problem says we're drawing 3 balls out of the bag, one at a time with replacement. Part A says find the probability that all the balls are blue. The reason I'm asking you this question is because there are certain probability questions where the word, like and or whatever, doesn't show up, but you need the word to show up so you know what formula to use. So what you do is rephrase the question. This is very important what I'm saying. Some problems, the harder problems, you have to rephrase the question so that you're able to use the formulas that you have. So let's see what this problem says. We're drawing 3 balls from the bag, one at a time without replacement. The question says, find the probability that all the balls are blue. We don't have a formula that says probability all. Okay, we don't have a formula like that. We have formulas that have the words or, the word and, the word not, which we haven't got to yet. So we want these words in our question, okay? And if they're not there, can you rephrase the question so that they are there, so that we can use a formula that we have? Okay, so let me say it again. The question is, find the probability that all the balls are blue. Now, when you're drawing more than once and you're going to rephrase the question, my advice to you is just tell me what's going to happen on each individual draw. So if all of them are blue, it means the first ball, finish my sentence, the first ball what?
Is blue.
Is blue. And now there's a very important word I need. So if all the balls are blue, the first ball is blue. What's the next word? And, right. It means the first, here, let me write this down. It means the first ball is blue and, keep talking.
The second ball is blue.
The second ball is blue. Keep talking.
And the third ball is blue.
Right. Okay. So sometimes you get questions like this where you have to rephrase it, and rephrase it by just telling me on each individual draw what happened. So if all of them are blue, it means the first one is blue and the second one is blue and the third one is blue. And because you said and, now I know it's an and problem. Okay, so it's a little more complicated problem. This example 16 I put in here so we could practice this rephrasing the question kind of thing. Okay, so the notation for this, you have to rephrase it in your mind and then go, oh, okay, they're asking for the probability that the first one is blue and the second one is blue and the third one is blue. So in the last problem, I gave you this, but in this problem, I gave you some words and you had to rephrase it and get it like this. But once you get that, then everything else should be the same as like the last example. These events are not independent, or at least we don't know, because we're drawing without replacement. So we have to use the longer and formula, which is the probability of the first times the probability of the second given the first. Someone tell me the third term. Probability of what?
Probability of the third. given the probability of the first and the second.
Don't write probability, just first and the second. Yeah. Okay, and then we calculate each one of these. Okay, on the first draw, what's the probability I get a blue?
4/10.
4/10. This one is about the second draw, and the first one was already blue. So we drew the first ball, it was blue. It's been removed. Let me remove a blue. And now we're drawing from this new bag. What's the probability I get a blue on the second draw?
3/9.
3/9. Then this probability says we're about to draw the third time, and I've already done this. The first one was blue, and the second one was blue. And they're not coming back in because we're drawing without replacement. So I have to remove 2 of the blues. So let's say I do that. And now I'm drawing from this bag. Let's probably get a blue out of this bag.
2/8.
2/8. Yeah. And then you multiply straight across. 4 times 3 times 2 is 24. 10 times 9 times 8 is 720. And that's part A of this example. Questions so far? Okay, let's do one more of these rephrasing questions. Again, we're drawing 3 balls, one at a time without replacement. Find the probability that none of the selected balls are blue. None of them are blue. And you got to rephrase that. What does it mean if none of them are blue? It means the first ball is what? I'm drawing 3. If none of the 3 are blue, the first ball is what?
Not blue.
Exactly. This is how you're going to write that. First ball is not blue. That line up on top means not, right? First ball is not blue. Keep talking. So if none of them are blue, the first ball is not blue. Now I need a word.
And the second ball is not blue.
Okay, and the second ball is not blue. Keep talking.
And the third ball is not blue.
Right. So you have to rephrase the question like that to yourself. This is an and problem, but the word and is not there. You rephrase it, and then you go, oh, the word, you see that the and is there. So if none of them are blue, it means the first one's not blue, and the second one's not blue, and the third one is not blue. So that's the question. First one is not blue, and the second one is not blue, and the third one is not blue. The line on top is what it means not. Okay, and then again, we're going to use an and formula. There's 2 and formulas depending on if the events are independent or not. They are not independent. We're drawing without replacements. So we're going to write independent with a question mark up here. And we'll use the longer and formula. Here's how it goes. Probability of the first. So you're going to write it like that, okay? Times probability of the second, given the first, times probability of the third, given everything you see before it. So I'm going to write B1 and B2 with lines on top. All right. Any questions on that much? All right. This is about the first draw. When I draw the first time, I'm drawing from the complete bag. What's the probability I get a ball that is not blue? The bottom is 10. And the top, you have to count the ones that are not blue. How many are not blue?
6.
6. Yeah. Okay. For this probability, we're about to do the second draw because you see a 2 here. So this has already happened. What does that mean? That means I've already drawn the first ball and it's not blue. So you have to ask yourself, what does the new bag look like? Well, it looks like the original bag, but one non-blue has been removed. So just erase a non-blue. Anything that's not blue here, I'll erase this. And now you imagine I'm drawing from this new bag. And if I draw from this new bag, what's the probability I get something that's not blue?
5/9.
I didn't hear the top number. What is it?
5.
5. Yeah, 5/9. Okay. There's 5 non-blues and there's 9 total. Now to get this probability, I'm about to do my third draw. Okay, so what's already happened? This has already happened. I've already drawn 2 balls. The first one was not blue and the second one was not blue. So I have to remove 2 non-blues. I already removed 1 non-blue. Let me remove another non-blue. It doesn't matter, any one that's not blue. And now you need to imagine we're drawing from the bag that you see there. And if I draw from the bag that you see there, what's will probably get something that's not blue?
4/8.
4/8. And then you multiply straight across. And the answer, let's see, 120 over 720. Okay, that's example 16. Questions? All right, so that's how that goes. All right, let's move on. Okay, so I'm just gonna do one of these. Example 17, you're gonna draw a single card from a deck of cards, and it says find all these probabilities. Let me just do, I don't know, I guess I'll do the second one. Let's just do this. So I'll do this one, I'll let you do the rest on your own. Again, this one could be done both two ways. Let's just go and use the AND formula. When you're drawing one card only, we don't know if the events are independent or not. So you're gonna write independent with a question mark. And that means you can use the longer AND formula that goes like this. Probability of the first times probability of the second given the first. Now remember, for this problem, we're only drawing one time. So it's not, someone might say, is it with replacement or without replacement? The answer is, doesn't matter, we're only drawing one time. Okay, we're drawing a single card. The first one says, let's find the probability of D, probability of getting a king. And since this is not a conditional probability, we're drawing from a full deck. Someone tell me the probability of getting a king.
4 out of 52.
4 kings, 52 total, yeah. But then for the second one, probability, it's a conditional probability, okay? So again, when it comes to doing something once and it's a conditional probability, it goes like this. I want you to imagine I drew a card out of a deck. I don't look at it, but I show it to you, and you tell me this information. You said, hey, Greg, it's a king. That's what you tell me. As soon as you tell me that, my new sample space, the only thing it could be now is king of clubs, king of diamonds, king of hearts, king of spades. Can't be anything else. So the bottom number is 4, because that's, you have to imagine the rest of the deck has just disappeared. With the new information you gave me, it's got to be a king. Now, to get the top number, probability of B, you have to count the black cards, but don't count how many black cards are in a full deck. Count how many black cards are in my new deck. How many black cards in the new deck?
2.
2. And again, you can multiply straight across, or you can cancel the 4s if you know that you can cancel the 4s. The answer is 2 out of 52. That could be simplified further. All those things are up to you. I don't need you to do that. That's the only part of example 17 I'm going to do. Let's see what it says here. A detective is trying to solve a murder case. At the outset of his investigation, he knows the murderer is one of the 200 people in the following table. And the question is, what's the probability the murderer is female and from Montebello? And, oops, so it's an and question. What's probably the murderer is female and from Montebello? Part of the reason I want to do this one is because there's some extra things you got to do in this one that you didn't have to do in the other ones. I've mentioned it before, but let me mention it again. So if letters are not given to you for events, then the very first thing you need to do is you need to write down some letters for the events that you care about in the question. Now, and then the second thing you have to do is you have to write down the notation. So all that stuff was done for you in all the examples we've done so far today, but not in this one, so I'm gonna have to do that. So it says, what's the probability the murderer is female and from Montebello? For the and, we're gonna use the and symbol. But whatever's before the word and whatever's after the word and, I need letters for those events. So you're gonna start off by saying, let F, I'll use F for female, let F be the event that the murderer is female. Okay. And then after the word and, it says Montebello, so I'm going to write let M. So M is for Montebello. Be the event that the murderer is from Montebello. So what I'm writing here, I need you to write. If it's not given to you, if I don't say this letter means this letter means this, if I don't do that in a problem, then you have to do that in the problem. And you don't have to make up a letter for every possible event. Just make up a letter for the events that are in the question. And since you see an and, just make up a letter for what's before and what's after it. Okay. Then the second thing you have to do, again, that was done in all the previous problems, but this time you have to do it, is you have to write down the mathematical notation for the question. So you got to take this question and write the math notation for it, which is not hard. It says, what's the probability? So you're going to put a P, that the murderer is female, and from Montebello. Okay, so just check this out. These two things that I did, writing the letters and writing the notation is 2 extra things you have to do in a word problem if they're not already done for you. But after you do those things, then the rest of it is the same as all the other examples. So let's go ahead and finish this now. Any questions so far? All right, so it's an AND problem. Again, there's 2 AND formulas. The one you use depends on if the events are independent. I don't know if they're independent, so I'm gonna write independent with a question mark. It actually turns out that in the video from last class, I proved that these events are independent. So if you knew ahead of time that they were independent, you can use the shorter AND formula. But if you don't know, then you can use the longer AND formula because it works all the time. Okay, so here's how the longer AND formula goes. Probability of the first times probability of the second given the first. Okay, the first probability says find the probability the murderer is female. So you got to count how many females are in the table and how many people are in the table total. The bottom number is going to be 200. That's how many people are in the table total, absolute total, 200 people. The top is how many people are female. How many people are female in the table?
60.
60. Yeah, you got to count all the females, all of them. So there's 45 and there's 15 more. 45 of them are from Montebello, 15 are from Pico Rivera, but you count all of them, 60. Okay, another reason I'm doing this problem is for this conditional probability part. I want to show you how to do a conditional probability when you're given a contingency table like this. So now, this is how this is going to work. This is new information. In other words, we know the murderer is female. Now figure out the probability the murder is from Montebello. So once they told you the murderer is female, it narrows down the sample spaces. The sample space is not the entire table anymore. If they say the murder is female, the murder is here somewhere in this green box. So everything that's not in the green box, any number that's not in the green box, we're going to ignore for the rest of it. It's like the bag got shrunk down to less things. Same thing here. The table got shrunk down. So all these numbers, forget about them now. They're gone. Okay, so then the bottom number is going to be how many people are left in the table, which is 60. Okay, 60 people total if you're just looking at the female column. And then how many of those people are from Montebello? How many?
45.
45, yeah. And then you can multiply straight across. I don't feel like doing that because the numbers are big. But if you cancel the 60, if you know you can cancel the 60s, cancel the 60s. And the answer is 45 over 200. And that is the end of the story on example 18. Questions? Okay, so that's all the examples I'm going to do as far as probability of ands go. So now we're going to go to probability of not. So remember, line on top means not. Probability of not A. This is actually pretty easy. Let me just give you a quick example here. Let's say the probability that it rains today. Rains today. Let's just use R for rains today, okay? So R stands for rains today. Whoa, what did I write there? Rains today. So let's say the probability it rains today is 20%. Then you tell me, what's the probability it does not rain today? You guys know the answer. Tell me. Probably it does not rain.
80.
80%. Right. Now, how did you come up with that? You probably thought, well, these have to add to 100 because either it's going to rain or it's not going to rain, and that's correct. Now, the correct, so you're totally right that it's 80%. Now, if you were going to, let me cross this off for a second, though. If you were going to use a formula for it, it would go like this. Like, how did you come up with the 80%? This is what you did. Even, you may or may not realize that this is what you did, but this is the way you write what you did. You take 100% and you minus the 20%. So from 100%, you take 20% away, and whatever's left, that's the probability. And the way you would write, so this is what you did, 100% minus 20%. That's how you got the 80%. Now the 20% is the probability that it rains. So this is basically a formula for how to find probability not. Take a look at this. Probability it does not rain. Anytime you find the probability of not, you'll put 100% minus, and then you'll put the same probability, but no line on top. So probably it will rain. Let me read this again. Probability it will not rain is 100% minus the probability it will rain. Okay, so that's the formula for it. Now, there's two different formulas for it. They're not really different, but let me just say it like this. If the probability is given to you as a percentage, like it is here, 20%, then write the formula like this with 100% written over here. Okay. If the probability is not a percent, if it's a decimal or a fraction or anything else, then instead of writing 100%, write 1. 100% is the same thing as 1. So the formula would go like this. Probability will not rain today is 1 minus probability it will rain. So which one do you use? Again, if it's percentages, if the probability is given as percentages, use this one. If it's decimals or fractions or anything else besides percentages, then you'll use the bottom one. They're basically the same formula. But I'm telling you that because sometimes I see people use this one when there's decimals and then things get weird. Okay, so that's all. But here's the formula. Okay, so probability not A is 1 minus probability A. So again, either you're going to put a 1 here or you'll put 100% here. Most of the time you'll put just a 1, but if the probability is given to you as a percent, then you put 100%. Now from this, we get this other formula for at least 1. But right now what we're going to do is we're going to do a couple of examples where we practice this formula here. Okay, here we go. We're just going to do this one example, and I'm probably not even going to do all of it. I'll just do part of it. Here it says we're going to play a single game of roulette and find the probability not A. A is the event the ball lands in an odd slot. I'm not asking you to find the probability that it lands in an odd slot. I'm asking you to find the probability it does not land. That means not. It does not land in an odd slot. That's what I'm asking. Now, this problem, like a lot of problems, can be done in two ways. I will show you two ways to do it. The first way is if you use the absolute value formula right at the beginning. So you can put a fraction line. Up on top, you're going to put whatever's in parentheses with an absolute value around it. On the bottom, you always put absolute value of S. And then you're going to count. This is the first way of doing it. Okay, absolute value of S. What's absolute value of S when you play roulette? Anyone?
38.
38. There's 38 different outcomes when you play roulette. Now over here, what I'm asking you to count, I'm asking you to count the slots, not the ones that are odd, the ones that are not odd. How many slots on the roulette wheel are not odd? No. 18 are odd. How many are not odd?
20.
20. Here, let me show you. So here's a roulette wheel. When they say odd, they mean from the numbers 1 to 36. So from the numbers 1 to 36, 18 are odd, and the other 18 are even. So how many are not odd? Not just the 18 evens, you have to also count the 2 greens. So there's 18 odd, there's 18 even, and there's 2 greens. If you're counting the not odds, you have to count everything else. So 18 even and 2 greens. So there's 20 slots that are not odd, the evens and the greens. Okay, so that's 20. Is everybody clear on the 20?
Yes.
Okay, and that's one way to do it. Let me show you a second way. The second way to do it is with the formula that I just gave you. Here's how the formula is going to go. Probability not A, you're going to write 1 minus, and then you're going to write the same thing it says here without the line above the A. So 1 minus probability of A. Probability not A is equal to 1 minus probability of A. And then I'm going to copy down the 1 and the minus, and I'm going to use the absolute value formula here. So this first way, use the absolute value formula in the first step. The second way, use the not formula, and then the absolute value formula in the second step. And then you start counting. I'm going to copy down the 1 and the minus again. 38 slots total. And what do I have to count here? It says absolute value of A. I have to count the slots that are odd. So make sure you guys understand the difference between the two ways I'm showing you here. If you do it this first way, you have to count the slots that are not odd. If you do it this way, you have to count the slots that are odd. Okay, so it all depends on, do you want to count the ones that are not something or the ones that are something? All right, how many slots are odd? So how many odd slots?
18.
18. So it's 1 minus 18 over 38. Now you could just do that on your calculator. But again, I'll spend a couple of seconds talking about fractions. When you're subtracting fractions, they're supposed to have the same denominator. So the trick is, since the second one has denominator 38, I want the first one to have denominator 38. So you write 1 as 38 over 38. 38 over 38 is 1. So I changed the 1 to 38 over 38. If you're confused by that, don't worry. Just type this in a calculator and be done with it. It's not important. But anyway, and then if you subtract fractions with the same denominator, that's the denominator of the answer. And then you get the top by doing 38 minus 18, which gives you 20. And you see we got the same answer. All right, that's how you do that one. We'll do one more example. Any questions so far? Okay, let's do this one then. Probability not C. This will be. I'm going to skip the third one. You guys can do that on your own afterwards. But let's do this one. I'll do this one 2 ways again. So first way to do this is with the absolute value formula right at the beginning. So whatever's in parentheses, you're going to write on top with an absolute value sign, and you're going to write absolute value of S on the bottom. And again, absolute value of S is 38. And on top, I have to count. What do I have to count? Well, C is the green slots, but I'm not counting the green ones. I'm counting the slots that are not green. How many slots on the roulette wheel are not green?
36.
36. Well, there's 2 green, right? So the other 36 are not green. And that's the end of the story on that one. And then the second way of doing it, let's see. So probability not green. So if we use the not formula, you're going to write 1 minus, and then you're going to write probability of C with no line on top. Probability not green is 1 minus the probability that it is green. Then we use the absolute value formula on this one. And then we count. Again, the bottom number is 38, but the top is saying, so this time I'm counting the slots that are green. So again, doing it this way, you count the slots that are not green. Doing it this way, you count the slots that are green. How many are green? How many are green? Tell me.
2.
2.
2. Okay, and then you just subtract those. If you want to write this stuff, you can write 38 over 38 minus 2 over 38 so that they have the same denominator. Then you subtract and you get 36 over 38. Again, if the fraction stuff I'm doing is confusing you, just totally don't worry about it, because that's not what the point of the class is. You can just do that on the calculator. I don't care how good or bad you are. I mean, I want you to be good at everything, but if you're bad at subtracting fractions, just let the calculator do that, but be good at probability. That's what I want. All right, so that's how that goes, and that's the end of that story. And now there's just one more that we need to talk about to complete the story, and that's probabilities of at least 1. So here's the formula. So the formula is probability of at least 1 equals 1 minus probability of none. So anytime you're doing a problem where it says probability of at least 1, you're going to be using this formula, and you're going to write 1 minus probability of none. Then when you get, so in other words, to figure out the probability of at least 1, you're going to have to figure out probability of none first. And to find the probability of none, every probability of none is an AND problem, as you'll see when we do examples. So every probability of at least 1 problem is really 2 problems. First, to find the probability of at least 1, you write this formula down. Then you have to separately find the probability of none first. And then when you do 1 minus that, you'll have the answer for probability of at least 1. Okay, so let's just look at a couple of examples of doing that. Okay, so in this example, it says we're going to play a single game of roulette 3 times. And the question is, what is the probability that at least one, see how it says at least 1 right there? At least one of the spins results in a ball landing in a green slot. So at least one of those 3 spins landed on green. Okay, so we're going to need some letters for some events. Now we need some room, so I'm going to write it over here. So we're going to say let G be the event that the ball lands in a green slot. Okay, so now every time the problem says to find probability of at least 1, first thing I want you to do is I want you to write probability at least 1 like this. And I want you to notice I left some space on the bottom. We'll go back and fill that in a minute. So then it's equal to 1 minus probability of none. And just like we did for at least 1, I want you to write none up here and leave some space on the bottom. Okay, and now what you're going to do is you're going to fill in the space with whatever the question says. It says at least one of the spins landed on green. So I'm just going to write at least one lands on green here. Whatever you put there, I want you to put in the other area that we left blank. So you can write lands on green. And before we continue, I want to focus on this part here for a second. When you do what I just said, so you fill in here whatever it says in the question, you fill in the exact same wording here. When you do that and you read this whole thing here, sometimes it's not going to sound like English. It's sometimes going to sound funny. If it does sound funny, then just read it and go, what did I mean? And then just fix the wording and, and then go from there. So you might have to fix the wording here. You might have to fix the English. It says none lands on green. In this case, all you have to do to fix the English is erase the S and write none land on green. That's English now, so that's fine. But again, sometimes it'll be fine. It'll sound fine the way it is, but other times it'll sound really horrible. And if it sounds really horrible, then go ahead and fix that. Okay. So the next thing you have to do is you have to find this probability of none. Now, to find a probability of none, you're going to have to do a separate calculation because probability of none is not, you're not going to be able to do it very fast. You're going to have to do a separate calculation. So let me just leave this alone for now and get some separate space here to work on the probability of none part. So I'm working on probability that none land on green. Okay, so you have to think, what does it mean if none land on green? Remember, we're spinning the wheel 3 times. If none of them land on green, what does it mean happened the first time? It means the first time it didn't land on green, so it's going to be probability that the first, okay, this would mean that it landed on green the first time. So the 1 is like the first spin, so, and G is lands on green. So this is like the first spin lands on green, but I want to say the first time it didn't land on green, so you put a little line up here, like did not land on green. Remember that line, that complement is the same thing as not. This is the first spin didn't land on green. But again, one more time, what does it mean if none land on green? It means the first one didn't land on green. And, so you have to put the word and in there. And the second one didn't land on green, so we're going to write it like this. And the third one didn't land on green. So like that. Okay. And every probability of none problem turns into an and problem like that. Now that it's an and problem, we have to decide how to do it depending on if and there's 2 different and formulas depending on if the events are independent or not. Are these events independent? And the answer is yes. I know it doesn't seem like it is. It might not seem like it is, but when we do drawing things out of a bag, if you draw with replacement, then they're independent, and if you draw without replacement, then they're probably not independent. Well, in this case, we're playing roulette over and over again. Think about it as every single time after the ball lands in a slot, that slot doesn't get removed, or you could think of it as getting removed and we put it back. Or another way to say it is, sometimes people say roulette wheels don't have a memory. They don't remember what the last roll was. So every single time, it's kind of like playing roulette is kind of like having a bag of 38 numbers and you draw one, but then you put it back before you play again. So anyway, so they're independent. So that means we get to use the formula where we just do the probability of each one and multiply. This is the probability of the first times probability of the second times probability of the third. Okay, what's the probability the first one does not land on green? Well, you know the probability that it does land on green is 2 out of 38. In other words, there's 2 greens out of 38. So the probability it does not land on green, there's 36 non-greens out of 38. So probably the first spin does not land on green, 36 out of 38. Times was probably the second one does not land on green. Remember, it's the same wheel. All the slots are still there, so it's 36 out of 38 again. 38 non-greens 36 non-greens, 38 total. What's probably the third spin does not land on green? 36 out of 38 again. So then you just multiply this out, and you get 0.8503. That's not the final answer. That's the answer for probability of none. We wanted probability at least 1, so it's 1 minus probability of none. So right here you have to just fill in this area here with that 0.8503. So back to the original question, you put a 0.8503 here, so this number goes here, and you get 0.1497. That's a probability at least 1 of the spins lands on green. Okay, let's look at another example. Okay, so in this example here, we're going to draw 2 balls out of this bag, 1 by 1 without replacement. Okay, and the first question is, what is the probability that at least one of the balls is blue? It says at least 1. Part B says, what's probably that at least one of the balls drawn from the bag is red? The third one is probably at least one of the balls drawn from the bag is prime. So just keep in mind what the experiment is. We're drawing 2 balls, 1 at a time without replacement, and these are all at least 1 questions. Okay, let's start with part A. So again, first thing you're going to do is you're going to write down the formula for probability at least 1. So probability at least 1. And I want you to leave some space down there for, you're going to fill in some stuff later. And then the formula is 1 minus probability none. And then again, you're going to leave some space down there because you're going to fill in something later. So you first write the formula like that. Then you fill in the rest of it, the blank spaces there, with what the question asks you to find. It says find the probability that at least one of the balls drawn from the bag is blue. So at least one of the 2 that you've drawn is blue. So at least one is blue is what I'm going to just fill in here. Try not to make it too long. At least one is blue. Whatever you write there, I want you to write the same thing here. So I'm going to write is blue over here. Okay, next thing is you're going to look at this part here and make sure that's English. It says, what's the probability that none is blue? Now, I know you read that and you go, that doesn't sound right. We need to fix it. And I'm sure you know what it is. You just change the word is to the word are. Probably none are blue. Okay, that's not a big problem there because it was pretty close to English. But some problems, it gets really bad. So anyway, I'll write are blue here. Okay, so then it's going to be 1 minus, and now I'm going to come back to it. So the probability of none, I'm going to figure out that answer, and I'm going to put it here when I get it. Okay, but we don't know it yet, so that's a separate calculation you need to do. Okay, so now I'm working on probability that none are blue. So remember, we're drawing 2 balls, and I'm saying none are blue. So that's the same thing as the probability that the first one is not blue. What does it mean? You have to ask yourself. We have to translate this. What does it mean if none are blue? It means the first one is not blue, and the second one is not blue. You see what I just said there? What I just said there had the word and in it. It also had the word not in there a couple times. So one more time. What does it mean if none are blue? It means the first one is not blue, and the second one is not blue. Okay, I'm going to need a letter. So at this point, let me go over here and write down B stands for the event that you draw a blue ball from the bag. And we'll put subscripts on that depending on which draw we're talking about. So remember, probably none are blue means the first one is not blue. Remember what I have there is that the first one is blue. So you put a line up here, that's the first one is not blue. And the second one is also not blue. Okay, so you translate the word none into an and problem. Okay, since it's an and problem, we have 2 formulas to use depending on if the events are depending on if the events are independent or not. And since we're drawing without replacements, it says without replacement here, probably the events are not independent, so we're going to have to use the longer formula. So it's going to be the probability the first one is not blue times probably the second event given the first event. All right, what's the probability the first one is not blue? Well, you can see there's 4 that are blue. That means there's 6 that are not blue. 6 non-blue over 10 total. The second one is a conditional probability. So remember, this has already occurred. So I want you to imagine we're about to draw for the second time, because you see a 2 there. And the first one we've already drawn has been drawn, and it's not blue. First one is not blue. So I want to see what the new bag would look like. Let's take the old bag and just scribble off something that's not blue. Something like 10. This is not blue. Imagine that's gone. And now we're drawing from this new bag here. So if you're going to draw from that bag, what's the probability you get one that's not blue? Well, in the new bag, I see 4 blue and 5 that are non-blue. So there's 5 non-blue, 9 total. And when you multiply that out, you get 30 over 90. If you write it as a decimal, it's 0.3333. And that's the answer for probability of none. So now back up top to find the probability of at least 1. It was 1 minus probability of none, so it's 1 minus this answer, 0.3333. So the point at the answer is 0.6667. All right, that's how that one goes. At this point, I want to mention something to you that this is a little bit cheating, but just a little bit of a hint. A lot of times in the homework and even on quizzes and exams, you might see the following. Because calculating a probability of at least 1 takes 2 steps, usually you'll see a question, find the probability of at least 1, come after a previous question where they made you find probability of none. So again, it's cheating, but it's just some idea to, keep in the back of your mind that if they ever ask for at least 1, go look at the previous question and see if you already did the none work so you don't have to do it again. Because in general, to find probability of at least 1, you have to do 2 things. You have to find the probability of none, which is an and problem, and then you got to do 1 minus it to get the probability of at least 1. All right, let's look at the next part of this example. Was it probably that at least one of the balls drawn from the bag is red? Basically the same question, but we changed the color to red. So I'm going to write let R be the event that the drawn ball is red. Okay. So now we're going to go ahead and write down the question. Remember, it's at least 1. So you start off by writing the at least 1 formula. Probability at least 1, and leave some space on the bottom, equals 1 minus probability none. So anytime you see an at least 1 problem, you start off by writing this formula. Okay, because it says at least 1 in the question there. Then you're going to fill in the bottom parts here with whatever it says. At least one of the balls is red. So I'm just going to write at least 1 is red. Whatever you fill in there, you put this exact same thing here. And then you go and you read the side and make sure it's English. It says none is red, and again, we're going to have to fix that. It's not a big deal. But we just have to change the word is to the word are. None are red. Okay, and then it's 1 minus, and again, I have to come back to this because probability of none is its own separate calculation. So we'll do that part here. The probability that none are red. And now you've got to think about that and go, what does that mean if none are red? Well, we're drawing 2 balls from the bag, remember? Draw 2 balls without replacement. If none are red, then it means the first one is not red. So you write it like that. And the second one is not red. Please remember, probability of none is always some kind of and, probability of an and. But you got to phrase it. It's the first one is not red and the second one is not red. Then since it's an and problem and we have 2 formulas for and, you have to decide which one to use. It depends on if the events are independent or not. We don't think that they are, so we're going to write it like that, independent with a question mark, because we're drawing without replacement, so probably they're not, but anyway, we're going to write it like that. That means we have to use the formula that has a conditional probability in it. It's going to be probability of the first event. Don't forget the not there, times probability of the second event, given the first event. And now we figure out what these numbers are. Okay, so probably the first one is not red. Okay, when you go to draw the first one, well, there's only one red. So how many non-reds are there? There's 9 non-reds. So 9 non-reds out of 10 total. But when you go to draw the second one, when you're doing this conditional probability here, this has already occurred. That means the first ball has been drawn out of the bag and it's not red. So the bag doesn't look like this anymore. It's like this, except one ball has been removed. And the ball that's been removed is a non-red. So the question is, if you draw from the new bag, what's the probability you get something that's not red? So I'm going to go ahead and just pretend, I'm going to cross off one of the non-reds as if we drew that one. So once again, let me just go ahead and just cross off the 10. It doesn't matter, just don't cross off a red, cross off a non-red. And now you imagine we're drawing from this new bag that has only 9 things in it. If I draw from that new bag, what's the chance I get something that's not red? Well, there's 9 things total in the new bag. And how many are non-red? Well, there's only one red, so there's 8 that are non-red. And the 9s cancel. You can simplify this to 8 out of 10. You could do more simplifying, but I'm just going to write it as a decimal, write 0.8. That's the answer to the probability of none, okay, 0.8. But now you take that answer and put it over here to get what we really wanted, probability at least 1. So it's 1 minus 0.8, which is 0.2. And that's the answer to that one. All right, let's try one more. So again, another at least one question. What is the probability that at least one of the balls drawn from the bag is prime? Okay, we're going to need a symbol for prime. I don't want to use P though, because we use P for probability. So I guess we'll just call it E. E is going to be the event that the ball is prime. Okay. So again, it's an at least one problem. So you're going to start off by writing the at least one formula. So at least one. Leave some space on the bottom, equals 1 minus probability none. Then again, you're going to fill in the bottom with what they're asking you in the question. They're asking what's the probability that at least one of the balls is prime. So I'm just going to put is prime down there. At least one is prime. Whatever it says there, we're going to write the same thing here, is prime. And once again, this is not English, so we're going to fix it. But it's a very small thing to fix. Just beware, in some problems it's really bad. You really got to fix it. In other problems, it's just fine the way it is. So instead of is prime, we're just going to change it to r prime. Okay, and then we're going to do 1 minus, now we've got to find the probability of none. So as I said, that's a separate calculation we have to do. So we'll come back to that. Well, down here we'll do probability that none are prime. And once again, you have to rephrase that. What does it mean if none are prime? It's an and. Remember, we're drawing 2. If none of the 2 are prime, it means the first one, this 1 would mean that the first one is prime. Remember, E is for prime. That's the first one is prime. So if I put a line up on top, that's probably the first one is not prime. One more time, if none are prime, it means the first one is not prime and the second one is not prime. So once again, a none problem is an and problem. None problems are always and problems. Okay, and then again, these events are probably not independent, so we're going to write it like this because we're drawing without replacement, so don't assume independence. So the formula then is the one that has the conditional probabilities. It's a probability of the first times a probability of the second given the first. All right, and now we start counting things. So this is the probability the first one is not prime. So if you draw from this bag, what's the probability the first ball you get is not prime? Well, the primes are 2, 2, 3, 5, and 7. The ones I've circled are prime. So let's probably get one that's not prime. Just count the rest of them to see the ones that are not prime. Looks like there's 6. 6 non-prime, 10 total. Okay, now let's work on this term here. Remember, this has already occurred. When you're doing conditional probability, that has already occurred. So I want you to imagine the first ball has been drawn out of the bag. It's not prime. We're about to draw again, and I want to know what's the probability the next one we draw is also not prime. So since we've already drawn one out of the bag and it's not prime, I want you to imagine removing one of the non-primes from the bag. Again, you can remove any non-prime you want. Let's go ahead and remove 10, for example. So that's not prime. And now when I go to draw again, I'm drawing from this new bag that only has 9 things in it, so the bottom number is 9. And among those 9, how many are not prime? Well, we still have the 4 primes, and we have 5 that are not primes. So I have a 5 up here. Yeah, so that's the answer to that. You can multiply it out. It looks like it's going to be 0.3333 again, just like one of the other parts. You put that number. So that's the answer for probability of none. So now if you want to find the probability of at least one, you put it up there, 0.3333, and you get 0.6667. And that's the answer to that one. Okay, guys, that's it for this video. Study hard, and I'll see you next time.